Hi, everyone. My name is Amy Wolf. I'm the programming coordinator for the Osterville Village Library. Thank you so much for joining us today on this a little bit frigid Saturday. I feel like I brought the cold air with me when I came back. And to our friends joining us on Zoom, thank you so much for being here as well. Today, we have the honor of introducing Jessica Sheppard as she gives a exciting, on the edge of my seat, lecture on the universe, from black holes to planets and everything in between. And don't be afraid to chime in at the end with any questions or thoughts. But without further ado, here's Jessica Sheppard.
Thank you, thank you, thank you. Come on in. There's space available. Come in. Brilliant. So caveat to all of you that are massive space nerds. I am not an astronomer. I am not an astrophysicist. I am not a mathematician. I'm simply somebody that's passionate about this subject. And just like when you go on family vacations or to Hawaii and you come back and you show everybody your slideshow and every single picture, this is going to be foisted on you in that same vein. My family won't listen to me anymore, so I'm very excited to be able to share with you a little bit and a snippet of how amazing it is to be a part of the universe. So Amy gave me 45 minutes here or so to kind of tell you about everything, which is absolutely impossible. So here is the universe in a nutshell for you. This is a fantastic photograph, most recently taken in 2019. And this is from the Hubble telescope, which is amazingly crystal clear for what we're able to show at this point, with the expanding idea of what is out there around us. But the idea of the universe and our place in it is a question that has constantly been on the mind of humankind. Ever since we've been able to look up into the heavens and the skies, it forces the question of, well, what am I in comparison to this? Like, why am I here? What's going on? How do things happen? And it creates questions, wonder, and awe. And it absolutely will give you a sense of size if you stare at it long enough, that you are a bit of nothingness compared to all of this. When we look up into the amazing, beautiful sky, what we're seeing are the stars that are closest to us, which in the most part will include the Milky Way. And the Milky Way is that hazy band of stars, a predominant swath that we see in the sky on a really good, clear night. And ancient folk were able to see this much, much more clearly than we could because they didn't have high skyscrapers, they didn't have city lights, they didn't have the light pollution that we have currently. If you do find a location that has the least amount of ambient light, a nice dark spot, when you look up on a perfectly clear night, you are only with your naked eye about able to see about 5,000 stars in the universe. And what they estimate is that there are close to about 400,000 billion stars. And that number is expanding, which is mind-boggling. How do you even picture a billion, let alone 400,000 billion? And that's of the medium-sized star. And that is 5,000 is quite a bunch for us to see. And that has to do with simply the view of the horizon due to the arc of the Earth and the fact that you are standing on one side of the planet and the rest of those stars are hidden behind you with the planet itself. So it is a very, very large, vast location. But even so, if we're able to look up and see that Milky Way, it's a very obvious set of stars that we can see in the sky. And the ancient people used to look up to this and try to put science and understanding into concept. They didn't have the tools that we have. They didn't have the telescopes that we had, but they had their vision of their eyes and they were able to tell stories. They were able to use the stars for navigation and placement. And the Milky Way was the first kind of heavenly body for them to be able to see and explain. Now, the Egyptians looked up at this and they said, that this is the great goddess Nut, and that her body is bending up over the heavens, as you can see here with her body and the stars. And she was the protector of the cosmos. And so the star shape that you see that is arching from horizon to horizon is that great protector of the people of Egypt. This concept, because the Milky Way is viewable from all places, more prominently in the southern hemisphere, was observed all the time. And when people were watching these mass migrations of birds, they saw that they were following the stars. And it became known as the bird pathway to many people in many languages. And I'm apologizing, this is not a very clear picture, but this is the Milky Way in perspective. And you can see the outline here in white that the Aboriginals called the Great Emu in the sky, that they were using as a reference point, seeing those darker areas that we now know are different types of nebulas. And they could picture in that a pattern of an emu. As far back as 750 AD, the group of people that are called the Tokeno, which are in the Colombian area of the northwest area of the Amazon, pre-Inca takeover, made beautiful pieces of pottery, and they were documenting their interaction with the Milky Way. And in this picture, there's a shaman right over here on the side that is connecting this arcing rainbow that you see of the stars. This is the Milky Way here, that they called the Ahipkondia, and that connected the heavens with the earth where the shaman is, and then these caves that you see underneath, which is the spirit world. And so this was a really important part of their culture. And it was so important that when they built their homes, it was in the same structure and shape and orientation as the Milky Way above them, so that they were emulating the sky into their dwellings. So it was really a critical part. In Japan and Korea, the Milky Way is known as the Silver River, or the River of Heaven. And what we're familiar with is the Greek description of the heavens. And this is a lovely painting that is depicting the story that Zeus had one of his plethora of children with a mortal woman, and wanted the child, which is Hercules, to become immortal. And while Hera, his wife, goddess of the gods, was sleeping, he placed Hercules on her breast to breastfeed. And she woke up and she said, "What is this?" And she pushed him away. And as he was ripped from her breast, milk spurted out. And that's how the Milky Way was created. And so our understanding, our terminology comes from the Greek and the Roman storylines. We call it the Milky Way today. But looking up into the skies, the Milky Way is one part of it, made of millions and millions of stars. But the closest star to us is our sun. And originally, people would look up into the skies and they thought that the sun was moving around the earth, that the earth was the center of the world, and the sun rose on the east and set on the west. We know that that is obviously not the case now. Thank you, Galileo Galilei, 1609, for inventing the telescope and putting that into placement for us. And so when we look at the sun, what we know now is that the sun is actually a star, and it's made out of predominantly hydrogen and helium gases. It is a burning, constant, flaring ball of gas in the sky that is a limited resource. This will inevitably burn out, as all stars will do. And what happens is that the sun is in the process of going through its life cycle. So it will continue to burn and flare, and every now and then have these larger flares when the movement of that gas gets into a greater pocket. And I have a quick little video, hopefully. I don't know what that was. Not that. To show you guys the actual movement of these solar flares. Maybe. Waiting for it. Making it larger. There you go. So as you see the sun rotating around, you'll see that gas every now and then heating to the point where there's this release of energy, a burst that comes off of the surface of the sun. Is that working?
Share.
Oh, we have to make sure we're sharing with everybody.
Is it this one?
This one. And now we're sharing. There we go. Okay. So these right here, from our sun, erupt, and we're able to see these. They last in very short amounts of time. They're usually about 20 or 30 seconds long when they're massive explosions. We don't have the effect here on Earth as far as the magnitude of the light or the sensation of the heat or the alpha particles that are exploding off of this until 8 minutes later. And that's simply due to the distance between the Earth and the sun. So if the sun did completely burn out, we wouldn't know for 8 minutes later, and then it would be completely black for us. But that's the distance that we're talking about between these. So these are called mass coronal ejections. And we now know that they can come in multiple levels, intensities, as you would. And there's the A class, which is not so bad, B, C, M, L, and then there's the X class. X class is the greatest and the most intense. And when those flare up, it has massive repercussions all the way onto the Earth. It impacts people that are on the ISS and the stations. When they can predict these and see them, NASA will give them a call and say, stop all exterior work. You need to come in. You have to shut all of the solar windows because it's so intense, the radiation that's coming out. It can damage and hit satellites. And when it hits Earth 8 minutes later and it's slowed down, that impact on the Earth is still so intense that it will end up causing massive blackouts. It will cause disruptions in your telephone because the electromagnetics are thrown off. So it is pretty intense and crazy. And in 1989, the entire province of Quebec went into a blackout for 12 hours because it just hit at the right angle and it wiped everything out from one flare, which is pretty amazing to think about. But we now have telescopes that are great, that we can train on the sun and we can watch and see these and we can see how intense they get and how big they are. Kind of a really cool thing to see. One of the cool side effects from this, how do I switch this back, Amy? Unshare.
Which one?
You want to be that. And then reshare. Yep, I'll figure that out. Beautiful. One of the other cool things as a side effect is that it creates the aurora borealis for us, or the northern lights. And a lot of people are familiar with this wonderful glow in the sky. This is the Milky Way with the aurora shining through this, just kind of a cool picture right here. So those charged particles that are coming off of the sun are huge levels of intensity. And when they come towards the Earth, they radiate out at us. And of course, they're going to hit the atmosphere of the Earth first, which is this big blanket around the planet, basically. And when it hits that gas level, some of them hit the gas and peer off. And what's really neat is that the Earth has our magnetic polarities. And so any particle that does penetrate into the atmosphere gets deflected to the poles. And it's like how neon works in a tube. When you have that gas that becomes excited through the electricity, the electron's going to bump to the higher level while it's intensified. And as it loses its energy, it jumps back down to its regular stable energy shell. And in the process of jumping down, emits light. Now, it depends on what gas is inside your neon tube. When you go down Route 66 and you can see purples and yellows and reds because they have neon or argon or krypton in them. And the same thing is happening in the atmosphere. Our atmosphere is 78% nitrogen. We've got 21% oxygen. We've got 0.92% argon. We've got krypton and a bunch of things in there. And it's also kind of like when you make firecrackers. You get the different colors from your firecrackers because you are exploding calcium or magnesium or sodium. And that's where you get the different colors. You get the colors of the aurora borealis by hitting those different gases in our atmosphere. So the sun flares, that beam of intensity comes, it hits our atmosphere, it excites the light, it bends to the poles, and then it loses energy. And what we end up seeing at different atmospheric heights are these different colorations that we end up seeing in the colors of the northern lights. Predominantly what we end up seeing with our eye, because the eye is used to and most sensitive to the wave spectrum light of green, are the green hues. But if you go further down towards the equator, you see, because of the bend of that polarity, you see the higher level of the atmosphere and you see more reds. But you can see a whole range of colors, and they move and they wiggle as these flares burn from the sun. The sky will look like it's waving at you. And it's really amazing to see. I lived in Alaska for several years and had the chance to see these, which was awesome. We'd go out all the time and see them and pop out, and it became almost commonplace, which is horrible to say. But one time that I went out, what was really, really amazing, out in the middle of a glacier that we had driven out to, hung out, had a blanket and everything set up, and spent several hours just watching the sky, was all of a sudden this very strange sound. And the auroras actually make a noise. And it's very, very rare to hear this noise. It's kind of like hearing lightning. Your odds and chances of actually hearing this is really low. So I was quite lucky. But what happens is that energy that's going through the atmosphere is intensified and then comes back down, in the same way of like rubbing your socks across the carpet and then discharging with your finger on the doorknob and you get that spark. That's what's happening in the sky. And that discharge through the atmosphere gives off an acoustic sound. And they say that it's similar to rustling papers, or the sound effect if you were to rub silk back and forth together. It's just this very gentle shushing noise that you'll hear, or a crackling sound. And that discharge is hitting the highest trees, like you would see here on the horizon, a building that might be nearby, or in my case, because I was in the middle of nowhere, it was actually my clothing, most likely. I was the tallest object, and so I could hear it close to where I was standing. I was zapped by the sun, which is so cool. In any case, the northern lights are due to our sun, which is really, really exciting. And this is kind of just a breakdown of those gases, and that gives you that color distortion based on which gas in the atmosphere is being energized.
I don't think of our atmosphere as going up.
Thinner and thinner and thinner, but yeah. Yeah. So if we think about what else is up in the universe, we can't ignore the idea of the moon. I will talk more about this for anybody that will be joining me on Thursday. Knock on wood that we have good weather at Dowses Beach when we do some stargazing. This is the heavenly body that we'll be able to see most prominently, one with your naked eye, two with binoculars, which a lot of people don't even think about using, but you can see so much in this. But the moon is a super amazing item, and it still draws and holds our fantasy. And if we look at it, we're constantly seeing the same face of the moon. The moon does not rotate, it only orbits. And we know that orbiting is going around the planet, whereas rotating is spinning. The Earth spins, which is why we have 24 hours in our day. But the moon keeps its same face pointing towards the Earth at all times. And it goes around the Earth 27 1/3 days. That's why you end up having a full moon twice in a month every now and then. It has a smaller orbit around us. But what's really cool is when you look up at this face on the bright side, the other side that we don't get to see is called the dark side of the moon. You'll notice that there are recognizable craters and patterns that are on this because it's been hit repeatedly over and over through asteroids and movements and rocks and debris. When we go to Dowses, I'll also point out, when you look at the full moon, you can actually see the landing location of several of the Apollo sites, which is really neat. People don't think that and look for them, but you can recognize and see them on a clear night. What we do notice about the moon, and what was noted years and years and years ago, is that continuous phase change. The moon will not be there. That's your new moon. And then as it increases, that crescent size is waxing until you reach the full moon, and then it decreases, and that's waning. And that's due to the shadow of the Earth being cast across it. This moon is just a rock. It doesn't have its own light source. It's just the reflection off of the Earth. And so you're just seeing this illuminated rock partially hidden by the shadow of the Earth. It's quite exciting. This one right here is the Tycho crater. It's the biggest dot that you see. If I go back, this one right here, if we enhance that, that's the Tycho crater that everybody can kind of recognize and see. Kind of a neat facet that's on the side of the moon that we can talk about later on. The moon is moving at 1,700 miles an hour, which is really cool to think about as it's orbiting around, and it's a neat one. So the cosmos are filled with these stars. And if we look at these stars and continue to concept the universe, this is my favorite vocab word of the week here, nova lunis. We were able to look into the heavens pre-technology and recognize patterns that were in the sky. And again, we're trying to make sense of what's above us. Where do we belong to this whole idea? And what they noted in the sky beyond the Milky Way, the sun and the moon, were these recognizable shapes that they could see in the sky. We now call those constellations. And the constellations were described to understand history and religion to people and the connections between why the earth or the seasons happened. You could say the gods were watching over you, and that gave people contentment, and they felt safer rather than the chaos of, oh my gosh, the world is so big and I am so little. It was also used for navigation when you're finding the North Star or the Polaris star, to be able to orient yourself and find your way home. So the constellations were a critical item to see in the sky. There are 88 different constellations that are named. And when we look in the skies, a lot of times we don't see them right away because of that light pollution. But when your eyes adjust and you're able to see them, you'll note that some of them are star patterns that have very, very bright stars, bigger stars, and little stars. And that's not because you have a big star full of lots of gas and a small star. It has to do with distance. And so just like our sun looks huge and big because it's so close to us, these stars are in different depths in the sky, but they look like a pattern from where we're standing. The next biggest star, if you ever look up in the sky, is Alpha Centauri. And again, numbers are really irrelevant, but it's 500 million light years away. It's big. And that's the biggest star in the sky. But if we look at these star patterns, again, we're not the first to recognize. This is Chinese scribing from the year 1000. And you can see up in the top, this one right here, the constellation that we might recognize, part of Ursa Major. Everybody knows that's the Big Dipper or Little Dipper. I can't read Chinese, so I don't know. But these were recognizable in the sky for sure. And when we look up, it's hard to see them, but this might be recognizable to us in the Northern Hemisphere. This is something that we see quite often, especially in the winter. Anybody know this one? Or if I add a little detail, Orion. Yeah. So you'll see the 3 stars across here, which is supposed to be his belt. And then this is up to his shoulder. And this is the other arm. And across here, this is where he's holding his mighty bow, the great hunter, or sometimes people have it as a head dangling. Yeah. But it relates back again to the mythologies of the skies. And so there are different types of apps and stargazers now that help you recognize in the sky. They'll superimpose pictures to make it more recognizable for you. And so here is Orion standing on the horizon. The story behind this one, real quick for you, if you don't know, is that Orion was originally a human. And he was a mighty, famous, wonderful hunter and so proficient at what he was doing that the gods were impressed and they would stop everything and watch him hunt. He and his 2 faithful dogs, Canis Major and Canis Minor. And as he was out hunting one time, he became tired and he took a nap against a tree. And as he stepped down to recline, he stepped on a scorpion. And the scorpion, of course, reached out and stung him and it killed him. And the gods were so devastated that they no longer had entertainment. They were just thinking that this was a wrongful death, that they decided to take that scorpion and throw it into the heavens, which is placed on the southern hemisphere. And Orion, they placed in the heavens to immortalize him forever, to be able to hunt across the great skies. And they put his 2 faithful dogs, Canis Major and Canis Minor, right next to him. And so that he could continue to hunt, if you go across from where his bow is, you'll see the lupus and the taurus, the animals for him to hunt into eternity. And it gives you the orientation in the sky, which is kind of neat. This slide that's here on the side gets a little bit more intense. If you do look into these constellations, like I said, they're in different sizes, but they're also in different colors now. And when we look at this in intensity, Orion's armpit, which is the star named Betelgeuse or Betelgeuse, is actually a really large star and it's yellow. And you can see that in intensity that's growing in that area. We know that Rigel, which is his kneecap right down here, is a blue star. And those different colors indicate different gases that those stars are made out of. So we not only know the distances of where they are, but we also know what they're made out of. And what's really cool now is that if we look into the belt on Orion, this is actually a star nebula. And nebulas are where stars are being created and born. So the gases are amassing together, and then they're so big in intensity, which is due to Newton's third law, everything has an equal and opposite reaction. When these gases amass, they then explode and push out further to new locations. And so this is where birthing stars are happening, and you can see the process of creation going on in the belt. Kind of a cool technology to be able to say. In perspective, similar to what I have here on the table, just to give you an idea of how big this star is to us, this is a proportionate picture by size, not by distance between these things. But there's the sun here in the upper area. It's Mercury, Venus, Earth, and the planets that go across. Similar, again, to like what I have up here on the table. And it's pretty intense. If we did put the planets just side by side so that their diameters were all touching, that distance is what's the distance between the Earth and the moon. So the size of the universe is a bizarre number, and it's hard to put into comparison, but maybe that gives you a little idea. So I do want to talk about the solar system. If we can expand this idea, the solar system, and then it goes into a galaxy, and then the galaxies then talk about the universe. That's your terminology. So if we start in our solar system, the closest planet to us is Mercury. There she is, beautiful and glorious. This is, again, a lot of the planets are named after the Romans and the Greek names because that's what we go with. That's our predominant English version of things these days. Mercury, everybody goes, oh, I know the order of the planets. I can sing-song them ever since 12th grade. I knew them all the way back in kindergarten. But there's some really kind of fun facts that we're now learning about Mercury. This is the smallest of the rock planets, and it's closest to the sun, and it's actually shrinking. It's the most pockmark covered, which should make sense because as debris is moving towards the sun, because the sun is so large in mass, it's got that massive pull of gravity, things are winging by and smashing into Mercury, so it's covered in dots and debris. And it actually, as it's orbiting, has a trail of sodium that goes around it. So when you take a picture of them, it looks almost like a baby tiny comet, and the tail end of it is this yellow dragon tail or wisp that comes off of Mercury. Kind of a neat planet. The next one that we can talk about is the lovely, beautiful Venus, the goddess of beauty, which is quite funny. She's the second star in the morning that you can see. She is the blue, hazy, star-like looking planet that you'll see up in the sky, sometimes called the morning dog or the dog star. And she's named after the beauty. But the reality is, if you were to land on this planet with a spaceship and open up the hatch and take a big, deep breath and be like, yay, I made it to Venus, the gases and the toxics that are on this planet are so intense you would drop dead. You could not even breathe. She's pure poison. And if for some crazy reason you were able to take a step off of your spaceship and take a step onto the rocky planet, you would immediately be crushed like a can of soda because the pressure is so intense in this location. So what scientists now call her is the closest thing to living hell in the solar system. She's not the beautiful blue planet that we think of her. She's actually quite dangerous. And she's the only planet that rotates in the opposite direction. All the other planets go this way, and she has to do her own thing, which is kind of ironic. The next planet, which is in our rocky planets, would be ours, the blue planet. What's this one called? You know? Earth. There we go. We got Earth. The only place that has life currently that we are recognizing, and that is due to our atmosphere and the fact that we have water. There are evidences of water on other planets, but we haven't found the life that correlates with that yet. But to have life, you have to have water, which is kind of exciting. This is in that Goldilocks zone in the universe. We're not too close to the sun that we're heating up, and we're not too far away that we're too cold, and therefore life was able to create here. And it's taken us 3.7 billion years to get to this point, which is pretty amazing. When we look at this rocky planet, we think of it as water and earth. But if we were to suck up all of that water and suck up all of that air, the rocky planet that would remain would be in proportion to what you see on the screen. There's not a whole lot of water. there is less oxygen around this. It is a very thin membrane that goes around the planet. So it's something to consider on how we take care of and treat and use, which is fodder for another lecture at some point. And the other thing to think about is that as we are hopping off of this and expanding our ideas of the universe and exploring the world that's out there, we are doing this with technology, and our technology is then running out, or we're using it in a wasteful way. And we are putting satellites up into the atmosphere, and those satellites go through orbit. And yes, some of them do come back down to Earth and they burn up as they re-enter into the atmosphere. But we have so much debris floating around the outside of our planet that if you were to look backward at the Earth now, rather than looking into the heavens and look at the Earth, it is fuzzy to the point where we have, too many things all over it. What happened to that slide? Oh, I have a picture that shows about 7,000 orbiting pieces of debris in the sky. NASA keeps a constant eye on about 3,000 of those pieces that are potential hazards. Objects of concern is what they call them, which could end up hitting the ISS station or become collated together to create mass enough that if they dropped into the Earth, they could hit and cause damage on the planet. And that is just our space trash that's floating up and around there. So that's only going to get bigger and bigger. Elon Musk is talking about putting up the Star Network, which would be about 7,000 extra satellites as well. So there's a lot of things floating around our planet from the outside. And the last rocky planet that we have is, of course, Mars. This is our closest in size. This is kind of our sister planet. This is the red planet, which means that she is really, really rusty. She's made out of iron. And we think that if she is red and rusty, that iron must have been exposed to water in order to rust. And so the water that we need for life has predominantly been found on Mars, which is kind of the next great, amazing thing to see. This one has two planets. They're called Panic and Terror, which is kind of neat, named after the Herculean side effects of going to Tartarus, and keeping in that Greek and mythology storyline. So after those rocky planets, we have the asteroid belt, and that's a big, huge minefield before we're able to go to a dwarf planet, which is known as Ceres. We actually have an extra planet in the solar system now, and that is a teeny tiny little one, basically a giant volcano, but it's frozen because of the distance from the Earth, which is kind of cool. And then we get into the gas giants that we're familiar with, Jupiter, and Jupiter is the largest of the planets. This is 11 times bigger than the basketball that I have on the table to give you a proportion in the size. There would be about 1,500 Earths that could fit inside of Jupiter. So it's really, really massive and big. And the hurricane that you see, the lips that are kissing Jupiter down here on that bottom space, her familiar birthmark, basically, that's actually a storm. And that migrates around the planet as she's orbiting and spinning around. We know now that Jupiter actually whistles. She makes a sound out in outer space. As she is spinning, these storms give off hydrogen, and that hydrogen has this really high-pitched sound, kind of like if you ever remember watching Roadrunner and Coyote, kind of that minute drops. That's what it sounds like as she rotates, and the satellite stays on one side of the planet and she rotates. So it picks up that sound effect. So it's a funny planet. And she also, as she's spinning, releases microwave levels of radiation off of her. So she sparks from the poles. So it's a very dynamic and active planet. The next one behind it is our ringed planets. And believe it or not, Saturn's rings are disappearing. So it will not always be the ringed planet. I'm so sorry to tell you. She's moving so fast that they're just flinging off and they're dissolving away. So it won't always look like this. Our lifetime it will, but inevitably it'll be gone. This is the lightest planet. If you were ever able to put this in enough water, she would actually float. The gas in the mixtures that she has are less dense than water. And she has 53 different moons around this planet all by herself. And if anybody has watched the Star Wars movie, and they're recognizing the Death Star, the giant robotic planet that they built with that depression that's in it, that was in tribute, in honor of the planet Minimus, which comes around this. So it's from reality that they used and copied for Hollywood. Our next planet in the solar system is Uranus. And Uranus is the coldest planet. This is actually tilted at a 90-degree angle. So instead of rotating, it actually rolls as it goes around and around. It's kind of off kilter a little bit, which is kind of crazy. If you wanted to visit this, it would take you 22 years going at light speed to even get there. So it's pretty far away. And when we talk about light years or years duration, we're using what is called the Universal Time Unit, UT1 or UT0. For anybody that used to study or look at time zones, or you know, you're winding your clock and you're trying to match Greenwich Mean Time, which is that lateral line, a longitudinal line that runs through Greenwich, England. That is passé terminology. There is no Greenwich Mean Time anymore. GMT, it's UT1. We talk about universal time because we self-centrically talk about how far things are off the planet. The next thing that they're trying to map out and figure out is the time difference between creating life or housing on the moon. And because it orbits at a different time than we do, how do you say, oh, meet me on Thursday, or we're going to send a payload to you. It'll be there at 2 o'clock. 2 o'clock your time, 2 o'clock my time. So we all now use universal time. The next planet is Neptune. There's a beautiful picture that we're getting off of the hues and the colors that we see from Neptune. This has the strongest windstorms of all of the planets. She's spinning at a speed which is incredibly fast. It's 4 times more intense than any hurricane that we've ever recorded on the planet Earth, with how fast the winds are moving on the surface. And when she has storms on this planet, in that turbidity, it rains carbon, and that carbon is condensed to the form of diamonds. So that's where I'm going. I'm going to visit this one. All the other planets you can actually see with the naked eye on certain nights. They look like stars to you. Uranus is, Neptune is the only planet distance-wise that now you would need to use a telescope to be able to see. And then we get back to the controversial Pluto. Pluto is a dwarf planet as of right now. This goes back and forth whether or not it's a planet or it's a moon or is it a real planet or whatever. We've now deemed it is a dwarf planet, meaning that it is too small to be a big kid planet, and it does not have its own independent orbit. Every several years, because Uranus is so close to it and so big with its own gravity, Pluto's orbit kind of gets sucked in a little bit into the orbit of Neptune and Uranus. And it's wobbly and wonky. And so it doesn't have its true own path in the sky. And therefore, we've said, okay, you're just this practice pretend dwarf planet, which is kind of crazy. And Pluto, actually, believe it or not, is maybe 2 planets. There's a rock that's next to it that is called Charon, and it was finally able to be distinguished between the 2 pieces. It's almost like this planet has a chunk that fell off. It's not an asteroid, it's not a meteorite, it's not moving. It's staying in tandem with Pluto. And so it's like a binary system that's going through the sky, which is kind of wild. So we have maybe 2 exoplanets, Ceres and Charon. And then we have the next asteroid belt that we know about now, which is the Kuiper asteroid belt. And beyond that, there's more planets that we now have in our solar system. So there's Hydra and Nix, which are a binary system. And then there's Eris, Mechmech, Cumula, Sedna, OR10, Quasar, and Ixion. Those will be in the school books in the coming future. But we're learning about those, and those are just extended in our solar system due to the fact that now we have technology that's able to see into these heavens. We can not only look up, but we can look back, we can look further, which is really exciting stuff. So with our technology, we're able to have this massive distinction up into the skies. 1899 was some of the first photography that was going on. This was from an amateur photographer, and he was able to see, oh my gosh, I can't remember the name of this one. I think this is part of the Andromeda Nebula. Apologies, I will look that up for you in a second. But from a telescope, he was able to take a photograph through the beam of the refracting telescope. And so that was an amazing picture that was published around the world. People were quite excited to see galaxies spinning in orbit in the distance. We know that the universe is expanding outward. It's in a linear format, but that linear format is in all points 360 degrees, and it is continuous. It is Andromeda. Thank you, Andromeda. It is continuously moving outward. Nothing that we have put out has bounced back to us, including radio waves, sound waves, light waves. Light does not return to us. We know that the Earth is, the universe is expanding outward. It's expanding outward, but it's also spiraling outward, which is kind of a crazy concept. Kind of similar, like, forgive me, rubber balloon. What I've drawn on this are the spiraling galaxies all over it. And if this was the universe in entity, that movement of those spirals, the spirals will expand and the balloon stretches and expands. So that's what happens continuously up there. As we gain in knowledge, it's getting further and further and further away. So distances that we describe have to be modified. So the movement of this is just bigger and bigger, and our plans and our fuel that we allot for to get to something has to be contingent. The technology with the microscopes and the telescopes that we have now, that's the same picture, but it's much, much more crisp and clear to be able to see what's going on without the ambient light or the radiant light that's coming off of that. When we send out these weather balloons, when we send out satellites, when we send out floating laboratories and we're collecting this kind of data, what we get back is amazing pictures, but it's also giving us evidence of what the planets are made out of, why I can give you those facts, why these stars are different colors. We now know that mainly the skies in the Milky Way are predominantly made with ethyl formulate gas, which is the same chemical that gives raspberries their tastes and rum their flavor. So you could take a scoop of the Milky Way and it would be delicious, which would be really cool. But it's all due to the advances in our technology. And what we have over time are these different forms. So we have the Very Large Array, because scientists are so unique with the names of their telescopes. This is a land-based satellite system. We have the Spitzer, the Hubble, the XMM Newton, and the Chandra, and most recently, the James Webb Space Telescope that's been put out. And what's really cool is each of these pieces of technology are taking photographs with different filters, basically. They are designed to pick up certain frequencies or wavelengths within the spectric wave of vision. And so if they were to take a picture of the same piece of space, we can then take those pictures and overlap them to get a more concrete idea of what's actually in outer space. So in my next picture, in the same spaces where you see here on the board, this is what the Very Large Array picture would take, where it's in the red wave spectrum. The Spitzer is more of a yellow, Hubble takes out the green, Newton blue, Chandra purple. And those are all taking a picture of the Crab Nebula. The James Webb Space Telescope, a little bit different that you see in the picture, that's the entire universe that we know of right now in one picture. And the angle of the lenses are to the point where it's able to bend and recurve in that space. And so our solar system being the very center, that's our sun, and that's everything, all the galaxies around us radiating out to the edge of known space, which is crazy to put in one picture. So if you take these pieces of evidence from the different technologies that are out there and you overlap them, the Crab Nebula, when we look at space, now looks like this. And you would think that that has been photoshopped, but that's just taking those different forms of light and pieces of information and giving us a little bit more understanding of what it is made out of and what it looks like. It's quite amazing with a lot of the pictures right here. This one is the Andromeda Nebula zoomed in, and it looks like exploding clouds, different gases. That's in the Taurus constellation. And these two pictures right here, this is the Eagle Nebula over on the left side. And when you zoom in the Eagle Nebula right there in the center, this is a very famous picture that's been taken from the Hubble telescope. This is known as the Pillars of Creation. And again, this is an area within a nebula where stars are being created and gassed and born. So we're able to see these kind of in depth due to really cool science that we have now. the next greatest, awesomest, coolest thing is called the Sloan Sloan Digital Sky Survey. And this is, if anybody's watched the Marvel movies and you've seen Tony Stark and he throws a thing into the air and then he's able to spin something with his fingers and expand it. And it looks like he's manipulating technology in the air, like a hologram. That's what this is actually doing. It's real life Hollywood. So this is the telescope piece that's over here, and it's taking pictures in multitude at ridiculous speeds of the entire universe. And it's been mapping this constantly. And when you take all of that information, just like you would with a GPS system or anything like that, what they've been able to do over on the right-hand side is to create the known 2-scale version of the entire universe. And then if you wanted to move your fingers and stretch it, you could zoom into our solar system, or you could collapse it, spin the Earth and zoom in over here and see what it looks like beyond Pluto or anything like that, which is wild. So this is an amazing piece of technology. And that's the Sloan piece. And from this, because we've been able to map this, what we're understanding now is that the universe that we can see, the visible pieces, is 5%. The other stuff, the space, for the lack of a better word, the black stuff that's out there where everything is just suspended, is actually stuff. And now that we have math and we have physics and we have quantum sciences, what we're understanding is that the entire universe is basically matter and energy. And matter, according to Einstein, E equals mc squared, matter is energy. So everything is energy. Light is energy, people are energy, matter is energy. And what we have is dark energy or dark matter. And so 95% of what is space is dark matter. And we know that it's there because it's responding to light, it's responding to gravity in weird ways, but it is reactive. And that dark energy and that dark matter is similar to you guys saying, well, I know it's windy because I can see the tree moving and branches are waving back and forth. I can't see the wind, but I can see the result of it. And that's how we know that black energy is up in the sky. And one of the amazing things is from the technology, from watching this, from looking at the mathematics, is that we are able to see black holes. And these are the first pictures that just came back as of 2019. These are the first pictures of an actual black hole. Black holes were theorized mathematically, drawn out on paper. Hey, I think this is a possibility. All the way back when Einstein was putting forward his ideas of relativity. And there was a 19-year-old kid at the University of Chicago that was like, well, if that's true, there should be these things called black holes. Again, to Newton's third law, for every action, there's an equal and opposite reaction. If you have a star that's going through this life cycle, burning and burning and burning, inevitably it's going to burn out. And as it's shrinking and burning out, it's going to reach this critical mass and it will expire. And when it expires, that gravity and that mass is so intense that it will push out and then pull in. And that's what the resulting black hole is this movement of everything back into the idea of nothingness, this point of no return. Light does not come back out of it. Gravity is so intense that black holes actually eat other black holes. There's different kinds. There's basic black hole, and then there's super hungry black hole, again, because scientists have wonderful names for things. Black holes that eat black holes, and supermassive black hole, which is the biggest. We actually have 2 black holes in the Milky Way close to us. Don't panic, they're far enough away. But what happens is that this intensity bends time and the space latitude that we were talking about, the idea that the universe is this continuous radiant flat. When it gets so intense because gravity is pulled to a point, it bends into that point. Now, when they were running the math out, everybody said, yeah, that sounds logical, but how are you going to take a picture of nothing? And how do you get a picture of black in black? Well, technology has moved along. We've been able to see it. And what we're noting now is that black holes look like this. And what you're looking at is in the very center, the black hole, and the ring that is around it is called, I can't remember this right off the top of my head. The center is the singularity, and that is the refracting light. So the light, because everything is bending inward, you're seeing the reflection from the backside. This is like a loop system. So the ring is actually the back or the bottom of the hole itself.
Thing that I have to reconcile, you say when a star burns up, which suggests its matter has been converted, that there's nothing left. But but conversely, you say, but there's a lot of stuff there and it's collapsing. So is it burned out and stuff, or is it not burned out, but a lot of me left and I'm condensed, you know?
This is the terminology between what we think of as matter because it's a visual item versus that idea of a dark matter piece. So it's burnt up and we no longer see the star, but there is this dark matter material source energy form that is out there that is having a gravitational effect. I know that doesn't answer what you want, but
No. I think matter, burning to energy is conserved, but it's going to then.
correct.
So
Where does it go? Yeah, yeah. And people think, well, if you do go into a black hole, do you come out? Are they the same thing as wormholes? And no, they're not. Wormholes are going to be something different, which is actually a tube through the rift of the space. And a black hole is, as of right now, a hole into nothingness. There is an unknown of where it is. We've never been able to put anything into one. We haven't been close enough to one to put machinery into it. Even if we can, the intensity of the gravity is so crazy from what we can predict that nothing would be able to survive to be able to say what was on the other side for us. So it's pretty wild.
You mentioned the bend.
Yep. Time is relative to your place compared to what's around you. And if your place stretches because you're being pulled in, an inch here is an inch here is an inch when you get closer to the black hole becomes this. So your distance changes and therefore the time that it takes you to move that changes as well. I know, it's math.
well, that's good.
Yes,
If you were to an endless entity, what's in between that black hole, which is also
terminology potentially. I mean, we talk about solar system to galaxy, multiple galaxies making up a universe. It's just a label that we've put onto it. Potentially, a black hole could be its own thing. Size is so relative, like irrelative. There could be universes within black holes. We don't know the answer to that. We need more science, more chances to go through. So I will leave you with the hope that you have Nova Lunis in you now and that you do want to stargaze. Next week is the Gemini meteor shower. There's supposed to be a prediction of about 1,000 meteors an hour, which will happen regardless if there's clear skies or not. We're going to hope for clear skies, but I will be down at Dowses Beach on behalf of the Osterville Library. And if anybody is interested in stargazing and looking at the moon and using the telescopes that the library has and a few of my own personal items, we can chat and see what's in the sky and see what's available. It's December and it will be 7:30 at night at Dowses Beach, exposed to the wind. So if you join me, I highly suggest you wear snow pants and bring a hot cocoa and a chair so that you can tilt back and stargaze and watch the skies. Stay warm, bring your mittens, and we'll see if we can see anything. And hopefully I'll be able to answer questions and explain what we're looking at up in the sky. The answer is 7:30, seven. The answer is 7. So, yes, my dear, question. We will be doing the stargazing on Thursday next week.
And I'll be there.
Any other questions for me? Yes,
I'm very
easy
hung-
questions, easy questions.
I'm very hung up on the distance between the Earth and the Moon being larger than the distance in all of this system. So why is it that we can see the moon much more clearly than we can see any of the other planets?
The distance that we're talking about from the Earth to the moon is this set distance. I think it's 187,000 miles. So it's relatively close. And that distance has the space to fit the diameters of the planets between it. But the planets themselves are actually spaced out into ridiculous light years distances. Yeah, I'm sorry, I wasn't clear on that.
I'm gonna be Thinking about that.
No,
Said 400 trillion planets, you were extrapolating, presuming the same density that those we can see.
correct. Yeah. And for the size of what is the average size of things and things like that. Yeah. Yes.
Any meteor shower causes, I think it's called Perseid meteor shower, but causes that meteor shower to occur every year at the exact same time at a time.
The meteors that are coming through are on their own orbit. The same way that Halley's Comet is coming through, and there's a predictability that you'll see that every 86 years. Yep. It's orbiting through the solar system, not the Earth. And so when it comes through that elliptical orbit and it passes through our atmosphere, we see it coming through timed wise at that origin where it's coming through the Perseid constellation. And so we've named it the Perseid shower. And it hits rhythmically in that same location, same timing to see. The meteors are basically rocks and debris and dust that are in the sky. And they're free and floating and all over the place normally. What happens is, just like that solar flare, is that it hits the atmosphere, and at such a phenomenal speed, it flings off or penetrates through. And so what we see is that burning movement, or that trail that comes off of it. And we see these very short bursts, a shooting star. It's actually a burning up piece of rock. And depending on the size, most of them are only about the size of a grain of sand. And they make those giant trails, which are amazing. But they're from a giant rock that's basically crumbling in space because it's whipping around. But we have meteorites that fall every single minute constantly right now. Like if you put a white piece of paper outside and you left it outside overnight, you could pick that up. And if you put a magnet underneath the piece of paper, since meteors are magnetic, anything that would be drawn to that magnet is considered a meteorite. So you could do this every single night and collect a jar full of them if you wanted to, which is kind of crazy. Yeah. Do I have questions on screen? Did I run out of time?